far beyond the familiar swirl of the Milky Way, far past the quiet glow of neighboring galaxies. There exists a distant system catalogued with a name that sounds more like a library entry than a cosmic wonder. UGC 12591. Not a poetic title, not a legendary name whispered in stargazing stories, just a number in a long astronomical catalog. And yet behind that quiet label lies one of the most astonishing galaxy mysteries astronomers have ever measured. UGC 12591 is not unusual because of its brightness. It is not famous for violent explosions or spectacular collisions. Instead, it is remarkable for something much calmer and far stranger. It spins. And it spins extremely fast. So fast, in fact, that according to what we normally expect from gravity, this galaxy should not be holding itself together at all. Imagine standing beside a massive cosmic carousel made of hundreds of billions of stars. As it turns faster and faster, the outward pull grows stronger. At some point, anything not tightly bound would begin drifting away into the darkness. Yet UGC 12591 continues its rotation calmly, as if the usual limits of gravity barely concern it. Before we travel deeper into this mystery, take a moment to settle in. Where are you listening from tonight? Is the night already quiet where you are? Or is the evening just beginning to soften? Perhaps you're lying comfortably under a blanket, or simply letting the slow rhythm of space stories guide your thoughts toward rest. Here on Velorin's Sleepy Space Mysteries, we often explore cosmic questions that unfold slowly, almost like quiet bedtime journeys through the universe. In fact, in another recent Velorin episode, we drifted through the strange emptiness of cosmic voids, vast regions where galaxies themselves almost disappear. Tonight's mystery sits at the opposite extreme. A galaxy so massive and so fast that it seems to push the boundaries of what gravity should allow. UGC 12591 lies about 400 million light-years away from Earth. That means the light reaching our telescopes tonight began its journey toward us long before the first humans ever walked across the planet. And yet, when astronomers finally examined that ancient light carefully, something unexpected appeared hidden inside it. A rotation speed so extraordinary that it raised a quiet question across astronomy. What is really holding this galaxy together? If you enjoy slow journeys through the mysteries of space, consider subscribing, liking the video, and joining our growing Velorin community. It helps this calm corner of the universe reach others who might appreciate a peaceful cosmic story at the end of a long day. And if you feel like sharing, tell us where you're watching from tonight. Now, let us slowly drift closer to the strange spinning mystery of UGC 12591 and the deeper secret of gravity it quietly reveals. To understand why the UGC 12591 galaxy challenges our expectations of gravity, we first need to explore how astronomers can measure the motion of something so unimaginably far away. After all, a galaxy hundreds of millions of light-years from Earth cannot be watched the way we watch planets moving across the night sky. A single rotation of a galaxy can take hundreds of millions of years. No human lifetime is long enough to see even a small fraction of that motion directly. Yet despite this limitation, Astronomers have developed remarkably precise methods for revealing the movement of distant stars and gas. The secret lies not in watching the galaxy move through space, but in carefully studying the light it sends toward us. Every star inside a galaxy emits light, and that light carries subtle information about motion. When an object moves through space relative to an observer, the wavelengths of its light shift slightly. If the object moves toward us, the wavelengths compress, shifting toward the blue end of the spectrum. If it moves away, the wavelengths stretch, shifting toward red. This phenomenon is known as the Doppler effect. You have likely experienced a similar effect with sound. When an ambulance drives past, its siren changes pitch as it approaches and then recedes. Light behaves in a comparable way, though the change occurs in wavelength rather than sound frequency. Astronomers capture the light from galaxies using powerful telescopes and pass that light through instruments called spectrographs. A spectrograph spreads the light into a spectrum, much like a prism creating a rainbow. Within this spectrum appear dark or bright lines corresponding to specific elements such as hydrogen, oxygen, and calcium. These spectral lines act like fingerprints, identifying the chemical elements present in the stars or gas clouds. But they also serve another purpose. By measuring how far these lines have shifted from their expected positions, astronomers can determine how fast the material emitting that light is moving relative to Earth. Now imagine observing a spiral galaxy from afar. One side of the galaxy's rotating disk will be moving slightly toward us while the opposite side moves slightly away. The light from one side therefore appears slightly blue-shifted while the light from the other appears slightly red-shifted. By measuring these shifts across many different points along the galaxy's disk, astronomers can construct a map of its rotation. Each measurement reveals the speed of stars or gas orbiting at a specific distance from the galactic center. These measurements are then plotted on a graph known as a rotation curve. On this graph, distance from the center of the galaxy runs along the horizontal axis, while orbital speed runs along the vertical axis. Near the center of a galaxy, speeds tend to rise rapidly. This makes sense because the gravitational pull from the dense central region accelerates the surrounding material. But what happens farther out is where things become interesting. According to the simple expectations drawn from systems like our solar system, speeds should gradually decrease with distance. Planets farther from the Sun move more slowly because the Sun's gravity weakens with distance. If galaxies behaved the same way, stars in the outer regions would orbit much more slowly than those near the center. However, observations reveal something quite different. Instead of declining, the rotation curves of many galaxies flatten out. This means that stars far from the center move at nearly the same speed as those much closer in. The gravitational pull required to sustain that motion implies that there must be far more mass present than we can see. This realization became one of the earliest clues pointing toward the existence of dark matter. When astronomers applied this same method to the UGC 12591 galaxy, they expected to see something similar to other massive spiral galaxies. Perhaps a rotation speed somewhere between 200 and 300 kilometers per second in its outer regions. That would already be quite fast by human standards. Yet the measurements told a very different story. The spectral lines revealed shifts corresponding to speeds exceeding 500 kilometers per second across large portions of the galaxy's disk. Such a number is difficult to appreciate in everyday terms. 500 kilometers per second means traveling from New York to Los Angeles in roughly 8 seconds. It means circling Earth more than 10 times in a single hour. And yet, in the UGC 12591 galaxy, entire regions containing billions of stars move at such velocities while remaining gravitationally bound to the system. At first, astronomers approached the measurement cautiously. In science, extraordinary results demand careful verification. The orientation of the galaxy had to be considered. If the galaxy were tilted relative to our line of sight, the observed Doppler shifts would represent only part of the true velocity. Astronomers therefore examined the apparent shape of the galaxy to estimate its inclination. A perfectly face-on galaxy appears circular, while a tilted one appears elliptical. By measuring this ellipticity, they could calculate the angle and correct the velocity measurements accordingly. Even after these corrections were applied, the numbers remained astonishingly high. The UGC 12591 galaxy was not merely rotating quickly. It appeared to be rotating faster than any spiral galaxy previously measured. And that realization led to a deeper question, one that touches the very heart of gravity itself. If the stars in this galaxy are moving so rapidly, what force is strong enough to keep them from drifting away into the vast darkness of intergalactic space? Once astronomers confirmed that the UGC 12591 galaxy was rotating at extraordinary speeds, the next step was to understand what kind of mass could produce such powerful gravitational influence. In any rotating system, motion and gravity must exist in balance. If the gravitational pull inward is too weak, stars will gradually drift away from their orbits. If gravity is strong enough, the system remains stable and the stars continue circling the center for billions of years. This delicate balance between outward motion and inward attraction is what allows spiral galaxies to maintain their elegant structures. To picture this balance more clearly, imagine again the idea of a spinning carousel. When the carousel turns slowly, riders feel only a gentle outward pull. But as the rotation increases, that outward force becomes stronger and stronger. In order to stay seated, the structure of the carousel must be sturdy enough to hold everything together. In a galaxy, gravity plays the role of that supporting structure. It is the invisible force that continually pulls stars inward, preventing them from flying off into space. The challenge arises when the rotational speed becomes extremely high. In the case of the UGC 12591 galaxy, the stars in the outer disk are moving at more than 500 kilometers per second. At that speed, the outward tendency created by rotation is enormous. For the galaxy to remain stable, the gravitational pull across its disk must be equally powerful. And since gravity depends on mass, this means the galaxy must contain an immense amount of matter. Astronomers therefore began estimating the mass of the galaxy using the rotation data they had gathered. The relationship between orbital speed and gravitational mass is well understood. The faster an object moves in orbit at a given distance, the more mass must exist inside that orbit to hold it there. By applying this principle to the rotation curve of UGC 12591, scientists could estimate how much total mass was required to keep the galaxy intact. The results were staggering. The total mass needed to support such high rotation speeds appeared to be several trillion times the mass of the Sun. That number alone places the UGC 12591 galaxy among the most massive spiral galaxies ever studied. For comparison, the Milky Way is thought to contain perhaps 1 to 2 trillion solar masses when its dark matter halo is included. UGC 12591 may rival or even exceed that amount. Yet mass estimates do not stop with the total gravitational requirement. Astronomers also attempt to calculate how much of that mass comes from visible matter. This includes the stars that produce the galaxy's light as well as the gas and dust distributed throughout its disk. By studying the brightness of the galaxy and applying models of stellar populations, researchers can estimate how many stars are present and how much mass those stars contribute. In the case of UGC 12591, the stellar population is indeed enormous. The galaxy may contain close to 1 trillion stars, making it several times richer in stars than our own Milky Way. Gas clouds and interstellar dust add additional mass, though usually much less than the stars themselves. When all of this visible matter is combined, the galaxy still appears impressively heavy. But even after accounting for every star and every detectable gas cloud, something does not quite add up. The gravitational mass required to explain the galaxy's rotation is still far larger than the mass that can be seen directly. In other words, the visible components of the galaxy provide only part of the gravity necessary to keep those fast-moving stars in orbit. If the galaxy contained only the matter we can observe, its outer regions should not be able to remain bound at such high velocities. This discrepancy is not unique to UGC 12591. For decades, astronomers have encountered similar mismatches in many galaxies. However, the difference between visible mass and gravitational mass becomes especially dramatic in systems with extreme rotation speeds. In UGC 12591, the gap between what we see and what gravity demands is unusually large. That gap leads naturally to a profound conclusion. The galaxy must contain far more matter than is visible through telescopes. Something unseen is contributing enormous gravitational influence across the galaxy's disk and far beyond its luminous edge. This unseen component is what astronomers call dark matter. Dark matter does not emit light, reflect light, or absorb light in any way that current telescopes can detect. It remains invisible to traditional observation, yet its gravitational effects are unmistakable. It shapes the rotation of galaxies, binds clusters of galaxies together, and influences the large-scale structure of the universe. For the UGC 12591 galaxy, the presence of dark matter is not merely a theoretical possibility. It becomes almost unavoidable when the rotation speeds are considered. Without a massive halo of invisible matter surrounding the galaxy, the extraordinary motion of its stars would be impossible to sustain. The galaxy that once appeared as nothing more than a faint spiral in a catalog now reveals itself as a vast system embedded within an enormous halo of unseen mass. And this halo may extend far beyond the visible boundaries of the galaxy itself, quietly governing the motion of everything within it. But this realization opens another mystery, one that stretches even deeper into cosmic history. If UGC 12591 is surrounded by such a colossal dark matter halo, how did that halo form in the first place? And why did this particular galaxy grow so massive while still preserving its spiral structure, when many galaxies of similar mass eventually become chaotic elliptical systems? Those questions lead us into the next chapter of the story, where the formation of galaxies themselves begins to unfold within the invisible architecture of the universe. To understand how a galaxy like UGC 12591 could possess such enormous mass while remaining calm and structured, astronomers must look far beyond the galaxy itself and into the deeper architecture of the universe. Galaxies do not form randomly in empty space. Instead, they grow within a vast framework that existed long before the first stars ignited. This framework is often described as the cosmic web, an immense network of filaments made primarily of dark matter that stretches across the observable universe. In the early universe, shortly after the first moments of cosmic expansion, matter was distributed more evenly than it is today. Tiny fluctuations in density existed, however, and these slight variations became the seeds from which all later structure would grow. Regions containing slightly more matter exerted a stronger gravitational pull on their surroundings. Over time, this pull attracted additional material, gradually forming dense knots connected by long filaments. These filaments and knots together make up what astronomers call the cosmic web. Dark matter played the leading role in this process. Because it interacts very weakly with radiation and ordinary matter, it began clumping together earlier than normal matter could. While ordinary gas remained hot and diffused in the young universe, dark matter was already gathering into gravitational wells. These wells acted like invisible scaffolding. When ordinary matter eventually cooled enough to collapse under gravity, it fell into these pre-existing dark matter structures. Galaxies therefore formed inside dark matter halos. A halo can be imagined as a vast, roughly spherical cloud of invisible particles surrounding the region where stars eventually gather. The visible galaxy that we see through telescopes occupies only the inner portion of this halo. The majority of the mass lies far beyond the bright spiral arms, extending deep into space where only gravity reveals its presence. In the case of the UGC 12591 galaxy, this halo appears to be exceptionally large. Its rotation speeds suggest that the halo contains several trillion times the mass of the Sun. Such an enormous reservoir of dark matter would have created a very deep gravitational well early in cosmic history. That deep well would have drawn in huge amounts of gas from the surrounding universe, gradually building the galaxy we observe today. Gas falling into a dark matter halo does not immediately form stars. First, it must cool and settle into a rotating disk. As the gas collapses toward the center of the halo, it begins to spin due to the conservation of angular momentum. This is the same physical principle that causes a spinning ice skater to rotate faster when pulling their arms inward. As the gas contracts, its rotation speeds up, forming the rotating disks characteristic of spiral galaxies. Over billions of years, dense pockets within this disk collapse further, igniting nuclear fusion and forming stars. Each generation of stars enriches the surrounding gas with heavier elements through stellar winds and supernova explosions. Gradually, the galaxy becomes more structured, with spiral arms emerging as patterns within the rotating disk. Yet not every galaxy follows the same path. Many large galaxies experience violent mergers during their growth. When two galaxies of similar size collide, their gravitational interactions can disrupt the ordered rotation of their disks. Stars are thrown into chaotic orbits, and the resulting system often becomes an elliptical galaxy rather than a spiral. Elliptical galaxies are common among the most massive galaxies in the universe precisely because mergers tend to erase disk structures. This is what makes the UGC 12591 galaxy particularly intriguing. Despite its enormous mass, it has retained a recognizable spiral form. Its disk remains organized, and its rotation appears smooth and stable. This suggests that its growth history may have been unusually calm compared with many other massive galaxies. Instead of experiencing frequent major collisions, UGC 12591 may have grown primarily through steady accretion. In this scenario, gas from the surrounding cosmic web slowly flowed into the galaxy's halo over billions of years. Smaller satellite galaxies may have merged with it occasionally, but no catastrophic event occurred that would have shattered the disk. This gradual growth would allow the galaxy to accumulate tremendous mass while preserving its spiral structure. The dark matter halo continued expanding as more matter gathered into it, deepening the gravitational well and allowing the galaxy's rotation to remain stable even as speeds increased. Another factor influencing the galaxy's structure is angular momentum. During the early stages of formation, tidal interactions between neighboring regions of matter imparted spin to developing halos. If the halo that became UGC 12591 acquired a particularly large amount of angular momentum, the gas falling into it would naturally form a rapidly rotating disk. That disk could then grow larger and more massive while maintaining its rotational support. Over cosmic time, the combination of a massive dark matter halo, steady inflow of gas, and relatively peaceful surroundings could produce exactly the kind of system we observe today. A galaxy containing vast numbers of stars, rotating with remarkable speed, yet remaining balanced and stable across hundreds of thousands of light years. Still, even within this framework, the UGC 12591 galaxy stands near the extreme edge of what astronomers expect spiral galaxies to become. Its mass, its rotation speed, and its preserved structure together push the limits of current galaxy formation models. And that leads to a deeper question. If the galaxy is so massive and spinning so quickly, what prevents its delicate spiral disk from becoming unstable over billions of years? To answer that, we must look more closely at the subtle balance between rotation, gravity, and the internal stability of galactic disks themselves. When astronomers study spiral galaxies, they quickly learn that rotation alone does not guarantee stability. A galaxy is not a solid while spinning through space. It is a vast gravitational ecosystem made of stars, gas clouds, dust, and dark matter, all moving through the same region but not physically connected. Each star follows its own orbit, guided only by gravity. When the system is balanced, the galaxy appears calm and structured. But when that balance shifts, subtle instabilities can grow and reshape the entire disk. In most spiral galaxies, rotation speeds fall within a range that allows their disks to remain stable for billions of years. The stars orbit in roughly circular paths around the center, and the galaxy maintains a relatively thin disk. Spiral arms appear not as fixed structures, but as density waves moving through the disk, gently guiding stars and gas into temporary patterns of brightness. These arms can persist for long periods, even though the individual stars inside them continue moving along their own orbits. But when rotation becomes extremely fast, as it does in the UGC 12591 galaxy, the situation becomes more delicate. The faster the disk rotates, the stronger the outward tendency becomes for stars to drift away from their orbits. If gravity were only slightly weaker than required, the disk would gradually begin to unravel. Stars would slowly migrate outward, and the ordered spiral structure would fade over time. To prevent this, the gravitational pull across the galaxy must remain strong and evenly distributed. This is where the dark matter halo plays an essential role. Unlike stars and gas, which are concentrated within the visible disk, dark matter surrounds the galaxy in a much larger and more diffuse halo. This halo extends far beyond the luminous edge of the galaxy, sometimes reaching several times the radius of the visible disk. Because of its enormous mass, the halo creates a gravitational field that remains strong even at large distances from the galactic center. Stars orbiting in the outer regions therefore continue to feel a powerful inward pull, allowing them to maintain high speeds without escaping into intergalactic space. In the case of the UGC 12591 galaxy, the halo must be particularly massive in order to support the observed rotation speeds of more than 500 kilometers per second. Another important factor in disk stability is the distribution of mass throughout the galaxy. If most of the mass were concentrated only at the center, the outer regions would experience weaker gravitational support. This would cause the rotation curve to decline rapidly with distance, similar to the orbital speeds of planets around a star. But the rotation curve of UGC 12591 remains high across a large radius, indicating that mass is distributed throughout a wide region of the galaxy and its surrounding halo. This extended mass distribution helps stabilize the disk. Gravity acts not just from the center but from a large volume of surrounding matter. As a result, stars throughout the disk experience a smoother and more uniform gravitational environment. This reduces the likelihood of severe instabilities developing within the rotating system. Even so, astronomers still consider the possibility that disks can evolve over time. Small disturbances within a galaxy can grow gradually. Gas clouds can collapse into new stars, spiral arms can shift position, and bars can form across the central regions of some galaxies. These processes are natural parts of galactic evolution. What matters is whether the overall structure remains coherent. In UGC 12591, the available observations suggest that the disk has remained relatively stable for a very long time. Its rotation curve is smooth, its structure appears symmetrical, and there are no obvious signs of major disturbances. This stability implies that the galaxy has maintained equilibrium between gravity and rotation for billions of years. There is also the question of how far a spiral galaxy can grow before its structure becomes unsustainable. Astronomers have long suspected that there may be an upper limit to the size and mass of spiral galaxies. Beyond a certain point, the processes that build galaxies begin to favor the formation of elliptical systems instead. Large mergers, for example, tend to disrupt disks and produce galaxies where stars move in more random orbits. Yet the UGC 12591 galaxy sits very close to that boundary. It is massive enough that many galaxies of similar scale might have become elliptical long ago. And still it remains a spiral system, rotating rapidly but maintaining its disk. This suggests that under the right conditions, spiral galaxies can grow larger and more massive than previously assumed. Perhaps its environment played a role. If the galaxy formed in a region of space with relatively few large neighbors, it may have avoided destructive mergers that would have scrambled its structure. Instead, it could have continued drawing in gas from the cosmic web, steadily adding new stars to its disk while preserving its rotational order. The picture that emerges is one of remarkable balance. The UGC 12591 galaxy is not chaotic or unstable. It is a carefully balanced system where enormous gravitational forces quietly counteract extraordinary motion. Its stars race around the galactic center at incredible speeds, yet the structure of the galaxy remains graceful and calm. And this brings us back to the deeper mystery introduced earlier. If the galaxy's stability depends so heavily on the presence of an enormous dark matter halo, then understanding that halo becomes essential to understanding the galaxy itself. What exactly is this invisible substance that dominates the mass of galaxies? And how does it shape not only individual galaxies like UGC 12591, but the structure of the entire universe? By the time astronomers had carefully measured the rotation of the UGC 12591 galaxy, verified the data, corrected for its orientation, and compared its motion with the amount of visible matter present, the conclusion became increasingly difficult to avoid. The stars and gas that telescopes could detect simply were not enough to explain the galaxy's extraordinary speed. Something far larger and far more massive had to be present, quietly shaping the motion of the entire system. And that realization leads directly into one of the most important ideas in modern astronomy: the existence of dark matter. Dark matter does not behave like ordinary matter. It does not glow with the light of stars, it does not form clouds of gas, and it does not gather into planets or asteroids. In fact, dark matter interacts with the universe in a very limited way. As far as current observations suggest, it does not interact with light at all. Photons pass through it without being absorbed or scattered. Because of this, dark matter cannot be observed directly with telescopes. It reveals itself only through its gravitational influence. This may sound strange at first, but in many ways gravity has always been our most reliable messenger of hidden mass. Long before dark matter was proposed, astronomers were already using motion to infer the presence of objects they could not see directly. The discovery of Neptune, for example, came from noticing small irregularities in the orbit of Uranus. The unseen planet revealed itself through gravitational influence long before it was visually observed. Dark matter follows the same principle but on a much larger scale. When astronomers analyze galaxies like UGC 12591, they begin with the visible components: stars, glowing gas, and dust clouds. These can be measured through their brightness, spectral signatures, and distribution across the galaxy. From these observations, researchers estimate the total mass of luminous matter. But when they compare that visible mass with the gravitational mass required to explain the galaxy's rotation, a significant difference appears. In the case of UGC 12591, the difference is especially dramatic. The visible stars may account for 1 trillion solar masses or so, which is already enormous. Yet the gravitational pull required to hold the galaxy together at its measured rotation speeds suggests a total mass several times larger than that. The missing mass must exist somewhere within the system, even though it cannot be seen. The most consistent explanation is that the galaxy is surrounded by a massive halo of dark matter extending far beyond the bright spiral disk. This halo acts as a gravitational anchor. It surrounds the galaxy like an invisible ocean, with the luminous stars floating within its central region. While the stars trace the graceful spiral arms we observe, the dark matter forms a much larger and more diffuse structure that defines the galaxy's true gravitational boundary. For UGC 12591, this halo must be extraordinarily large. Its gravitational pull must remain strong far out into the galaxy's outer regions, allowing stars there to maintain speeds of more than 500 kilometers per second without escaping. The halo likely extends several 100,000 light-years from the galactic center, far beyond the visible edge of the spiral disk. Once astronomers include this invisible halo in their models, the galaxy's rotation begins to make sense. The extreme speed is no longer mysterious. It is simply the natural consequence of a galaxy embedded in an unusually massive dark matter structure. The stars move quickly because the gravitational well surrounding them is incredibly deep. Yet this explanation also opens another layer of questions. Dark matter may account for the galaxy's stability, but it remains fundamentally mysterious. Scientists still do not know exactly what dark matter is made of. Various theoretical particles have been proposed, ranging from weakly interacting massive particles to extremely light particles that behave more like waves than individual objects. Experiments on Earth continue searching for direct evidence of these particles, but so far none have been confirmed. Even without knowing its precise nature, however, dark matter has become a central component of our understanding of the universe. It explains the rotation curves of galaxies, the motions of galaxy clusters, and the large-scale patterns seen in the cosmic web. Observations suggest that ordinary matter, the kind that forms stars and planets, represents only a small fraction of the universe's total mass. Dark matter appears to make up the majority. In this context, the UGC 12591 galaxy becomes more than just an unusually fast rotating system. It becomes a powerful example of how invisible structures shape the cosmos. The galaxy's graceful spiral arms and luminous stars represent only the visible surface of a much larger gravitational framework. And that framework may hold clues about how galaxies grow, evolve, and survive across billions of years. The deeper we look into galaxies like UGC 12591, the more we realize that the universe is guided not only by what shines, but also by what remains hidden. The stars tell part of the story, but the unseen mass surrounding them tells the rest. And as astronomers continue studying this extraordinary galaxy, they are not only trying to understand why it spins so fast. They are also trying to understand what its immense dark halo reveals about the invisible architecture of the universe itself. By now, the story of the UGC 12591 galaxy has revealed something both surprising and quietly profound. A galaxy rotating faster than almost any other spiral system known is not tearing itself apart. Instead, it remains calm and organized, its trillions of stars continuing their long orbits through space. The explanation appears to lie in a vast halo of dark matter surrounding the galaxy, an invisible structure whose gravity anchors everything inside it. But this realization leads naturally to a deeper question. If such an enormous halo exists around UGC 12591 today, where did it come from? To answer that, astronomers must travel back in time to the earliest stages of galaxy formation. The universe began in a hot, dense state nearly 14 billion years ago. In those early moments, matter and energy filled space in an almost uniform distribution. Yet, even within that near uniformity, there were tiny fluctuations in density, small regions that were slightly heavier than others. These differences were extremely subtle, but over time gravity began amplifying them. Areas containing slightly more matter pulled in additional material from their surroundings, growing denser and more influential. Dark matter played a central role in this process. Unlike ordinary matter, dark matter did not interact strongly with radiation in the early universe. While normal matter remained tightly coupled to the intense background light that filled space, dark matter was free to move under gravity alone. This allowed it to begin clumping together earlier than ordinary matter could. Slowly, vast structures of dark matter began forming throughout the universe. Over millions and then billions of years, these clumps connected into a network of filaments and dense intersections. This structure, known as the cosmic web, stretches across unimaginable distances. Galaxies are not scattered randomly within this web. Instead, they tend to form at the intersections of these dark matter filaments, where gravity draws large quantities of matter together. Each intersection becomes the center of a dark matter halo. These halos are enormous, often extending hundreds of thousands of light years or more in every direction. Within them, ordinary matter begins to gather. Gas flows inward along the filaments of the cosmic web, falling into the gravitational wells created by dark matter. As the gas accumulates, it begins to cool and collapse toward the center of the halo. During this collapse, something important happens. The gas begins to rotate. Even tiny amounts of initial motion become amplified as the material contracts inward. This is a natural consequence of angular momentum conservation. Just as a spinning figure skater rotates faster when pulling their arms closer to their body, collapsing gas spins faster as it moves toward the center of a gravitational well. Eventually, the rotating gas settles into a flattened disk. Within this disk, regions of higher density begin forming stars. Over time, billions and then hundreds of billions of stars ignite, gradually building the luminous galaxy we can observe with telescopes. The spiral arms that we see in many galaxies are patterns created within this rotating disk as density waves move through the gas and stars. For the UGC 12591 galaxy, this process likely occurred within an especially massive dark matter halo. If the halo that formed in this region of the cosmic web was unusually large from the beginning, it would have drawn in tremendous amounts of gas over cosmic time. That gas could then form stars gradually, building an enormous stellar disk without requiring dramatic collisions or violent disruptions. Another key factor in galaxy evolution is the environment surrounding a galaxy. In crowded regions of space, galaxies frequently interact and merge with each other. These encounters can distort their shapes, trigger bursts of star formation, and sometimes destroy spiral structures altogether. When two large spiral galaxies collide, the result is often an elliptical galaxy where stars move in more chaotic orbits. The UGC 12591 galaxy, however, appears to have avoided many of these disruptive events. Observations suggest that it resides in a relatively quiet region of space where major mergers have been rare. This calmer environment would allow the galaxy to continue growing slowly by drawing in gas from the surrounding cosmic web rather than through violent collisions with other galaxies. Over billions of years, this steady process could build an enormous system. The dark matter halo grows as additional matter accumulates within it. The stellar disk expands as new generations of stars form, and the galaxy's rotation becomes faster as its total mass increases. What makes UGC 12591 so remarkable is that this growth appears to have continued for an exceptionally long time without destroying the galaxy's spiral structure. Many galaxies that become extremely massive eventually lose their disks and transform into elliptical systems. Yet UGC 12591 has remained a spiral galaxy despite its extraordinary size and speed. This suggests that its history may have been unusually smooth. Instead of undergoing frequent disruptive mergers, the galaxy may have experienced a long period of quiet evolution. Gas flowed inward along the cosmic web, star formation proceeded gradually, and the dark matter halo continued deepening its gravitational well. As this happened, the galaxy's rotation naturally increased. More mass meant stronger gravity, and stronger gravity allowed stars to orbit at higher speeds while remaining bound. Over time, the UGC 12591 galaxy became one of the fastest rotating spiral galaxies ever observed, not because it broke the rules of gravity, but because it formed within an exceptionally powerful gravitational environment. Yet even with this understanding, one puzzle remains quietly waiting in the background. If dark matter halos are responsible for shaping galaxies, why do only a few galaxies grow as large and fast as UGC 12591? What conditions allowed this particular halo to become so massive while others remain smaller? The answer may lie in subtle differences within the cosmic web itself, and in the quiet history of how matter flowed through the universe long before this extraordinary galaxy ever formed its first stars. Although spiral galaxies are among the most beautiful and recognizable structures in the universe, the largest and fastest examples of them are surprisingly rare. The UGC 12591 galaxy sits near the extreme edge of what astronomers observe in spiral systems. Its enormous mass and extraordinary rotation speed place it in a category that only a handful of galaxies approach. Understanding why such systems are uncommon helps reveal more about the delicate balance that shapes galaxy evolution across billions of years. To begin, it helps to remember that galaxies grow through two primary pathways. One is gradual accretion, where gas slowly flows into a galaxy from the surrounding cosmic web. The other is merging, where two galaxies collide and combine into a larger system. Both processes occur throughout cosmic history, but they influence galactic structure in very different ways. Gradual accretion tends to preserve order. Gas drifting into a dark matter halo cools and settles into a rotating disk, allowing spiral structure to form and persist. Star formation continues steadily, adding mass while maintaining the galaxy's organized rotation. If this process continues long enough without interruption, the galaxy can grow very large while remaining a spiral. Mergers, on the other hand, are far more disruptive. When two galaxies approach each other, their gravitational fields begin to distort both systems. Stars are pulled into elongated tidal streams, gas clouds collide and compress, and vast bursts of star formation can ignite. If the galaxies are similar in size, the collision can completely scramble the original disks. Instead of rotating smoothly within a thin plane, stars begin moving in many different directions. The final result is often an elliptical galaxy where the organized spiral structure has disappeared. This is why many of the most massive galaxies in the universe are elliptical rather than spiral. Over cosmic time, large galaxies tend to merge with others of similar size. Each major merger increases the total mass but reduces the likelihood that a stable rotating disk will survive. The more mergers a galaxy experiences, the more chaotic its stellar orbits become. UGC 12591 appears to have followed a different path. Despite its immense mass, it still possesses a disk and spiral structure. This strongly suggests that it has avoided major mergers for a very long time. Instead of colliding violently with other large galaxies, it likely grew through quieter processes. Smaller satellite galaxies may have been absorbed occasionally, but these events would not be powerful enough to destroy the overall disk. Another important factor is the role of angular momentum. When galaxies form, the rotation of their dark matter halos and infalling gas determines how large their disks can become. If a galaxy begins with relatively high angular momentum, the gas settling into its halo spreads outward before forming stars. This produces a wide rotating disk rather than a compact bulge-dominated system. For UGC 12591, the initial conditions may have favored exactly this outcome. Its halo may have acquired a large amount of angular momentum during the early stages of cosmic structure formation. As gas fell inward, that angular momentum would cause the material to spread into an extended disk while continuing to rotate rapidly. Over billions of years, this disk could accumulate enormous mass while maintaining its rotational stability. The surrounding environment also plays a quiet but important role. Galaxies located within dense clusters often experience frequent gravitational encounters with neighbors. Even if direct collisions do not occur, these close interactions can disturb disks and trigger structural changes. Tidal forces from nearby galaxies can warp disks, induce bars, or strip away gas needed for future star formation. UGC 12591, however, appears relatively isolated compared with galaxies inside crowded clusters. In such a quieter region of space, the galaxy would have far fewer disruptive encounters. Gas from the cosmic web could continue feeding the system without being stripped away by neighboring galaxies. This steady supply of material could help maintain star formation and allow the disk to expand gradually. All of these conditions together may explain why galaxies like UGC 12591 are uncommon. To reach such enormous mass while remaining a spiral galaxy requires a combination of circumstances that rarely occur simultaneously. A massive dark matter halo must form early in the universe. The galaxy must accumulate gas steadily without suffering major mergers. It must also maintain sufficient angular momentum to preserve a rotating disk rather than collapsing into a bulge-dominated system. When all of these factors align, the result can be a galaxy of extraordinary scale and motion. The stars continue orbiting in an organized disk while the surrounding dark matter halo provides the gravitational strength needed to sustain extremely high rotation speeds. UGC 12591 may represent one of the clearest examples of this delicate balance between growth and stability. Yet its rarity also makes it especially valuable to astronomers. Outliers like this help scientists test the limits of their theories. If galaxy formation models can reproduce systems as extreme as UGC 12591, those models become more reliable in describing how the universe evolves. If they cannot, it means our understanding of cosmic structure still has important gaps waiting to be filled. And so the story of this galaxy becomes more than a curiosity about speed. It becomes a quiet experiment written across hundreds of thousands of light years, revealing how gravity, dark matter, and cosmic history combine to shape the grand architecture of galaxies. If the UGC 12591 galaxy grew inside an unusually massive dark matter halo and avoided destructive mergers, another question naturally follows. What gave this galaxy the extraordinary rotation it still maintains today? Why do its stars move so quickly around the center, faster than almost any other spiral galaxy astronomers have measured? The answer lies in a subtle but powerful property of the universe known as angular momentum. Angular momentum describes the tendency of a rotating system to keep rotating. It is the same principle that allows a spinning top to remain upright or a bicycle wheel to stay balanced while turning. In astronomy, angular momentum plays a central role in shaping everything from planetary systems to entire galaxies. Once a large cloud of matter begins rotating, that motion tends to persist unless some force slows it down. In the early universe, as dark matter halos formed and began gathering ordinary matter, Small gravitational interactions between neighboring regions introduce tiny amounts of spin. These early motions were extremely gentle. But because galaxies grow through collapse and accumulation, even small initial rotations could become significant over time. Imagine a vast cloud of gas slowly falling inward toward the center of a dark matter halo. As the cloud contracts, its rotation gradually speeds up. This happens because the same amount of angular momentum becomes concentrated into a smaller and smaller region. A familiar analogy is a figure skater pulling their arms inward while spinning. As their body becomes more compact, their rotation accelerates noticeably. The gas falling into the halo that would become the UGC 12591 galaxy likely behaved in a similar way. Over millions of years, the cloud of gas contracted toward the center while spinning faster and faster. Eventually, it flattened into a rotating disk where stars could begin forming. Because the halo itself was extremely massive, it continued pulling in additional gas from the surrounding cosmic web. These cosmic filaments act like slow-moving rivers of matter. Gas flows along them toward dense regions of the universe where dark matter halos are strongest. If a galaxy sits at the intersection of several filaments, it can receive a steady supply of fresh gas over billions of years. This inflow not only increases the galaxy's mass but also contributes additional angular momentum to the disk. For UGC 12591, the inflowing gas may have carried particularly high angular momentum. As new material joined the galaxy's rotating disk, it added to the overall spin of the system. Over time, the galaxy's rotation curve would rise as both its mass and angular momentum increased together. The deeper the gravitational well of the halo became, the faster stars could orbit while remaining gravitationally bound. Another quiet contributor to the galaxy's rotation is the way dark matter halos themselves rotate. Although dark matter particles move in complex orbits rather than forming a rigid spinning structure, the halo as a whole can possess net angular momentum. When gas collapses into such a halo, it tends to inherit that rotational motion. This inherited spin helps determine the eventual size and speed of the galaxy's disk. A halo with high angular momentum allows gas to spread into a large rotating disk rather than collapsing directly into the center. The resulting galaxy becomes wide, thin, and fast rotating. In contrast, halos with lower angular momentum tend to produce galaxies dominated by central bulges rather than extended disks. The UGC 12591 galaxy appears to be an example where the combination of halo mass and angular momentum reached unusually high levels. Its dark matter halo provided a deep gravitational well, while its rotational momentum allowed the galaxy to form a massive disk instead of collapsing inward. Over billions of years, these factors work together to produce one of the fastest rotating spiral galaxies known. Yet there is another subtle influence that helps maintain the galaxy's extraordinary speed. The distribution of mass across the galaxy's disk also matters. If too much mass accumulated at the center, the disk could become unstable or form a large central bar that redistributes angular momentum. But observations suggest that UGC 12591 maintains a relatively balanced distribution of stars and gas throughout its disk. This balanced structure allows angular momentum to remain spread across the galaxy rather than concentrating excessively in one region. As a result, stars in the outer disk can continue orbiting at extremely high speeds while still following stable paths around the center. Over cosmic time, this balance between mass, gravity, and angular momentum has allowed the galaxy to settle into a remarkable equilibrium. The stars move rapidly, yet the system remains calm. The disk spans hundreds of thousands of light years, yet its rotation stays smooth and organized. When astronomers observe UGC 12591 today, they are seeing the outcome of processes that began billions of years ago. The galaxy's extraordinary speed is not the result of a recent event or sudden acceleration. It is the natural consequence of a long history of gradual growth within a powerful dark matter halo combined with the quiet persistence of angular momentum. Still, even with this understanding, the galaxy continues to raise deeper questions about the limits of spiral galaxies themselves. If a system can spin this fast while remaining stable, how close is it to the maximum possible rotation a spiral galaxy can sustain? That question leads us toward the next part of the story, where astronomers explore the boundaries of galactic stability and ask just how fast a galaxy can spin before gravity can no longer hold it together. When astronomers look at the UGC 12591 galaxy and measure stars orbiting at more than 500 kilometers per second, an important theoretical question naturally arises. Is there a maximum speed that a spiral galaxy can rotate while still remaining stable? In other words, how fast is too fast for a galaxy held together by gravity? To approach this question, scientists begin with a simple idea. Every rotating system must maintain a balance between two influences. One is the outward tendency created by motion, often described as centrifugal effect. The other is the inward pull of gravity. As long as gravity remains strong enough to counter the outward motion, objects remain bound in orbit. If rotation becomes too strong relative to gravity, the system begins to lose stability. In smaller systems like planetary orbits, this balance is easier to imagine. A planet moving too fast can escape the gravitational pull of its star. The escape velocity of Earth, for example, is about 11 kilometers per second. Any spacecraft reaching that speed can leave Earth's gravitational influence entirely. In galaxies, however, the situation becomes far more complex because the mass is spread across enormous distances and consists of billions or trillions of individual objects. Stars in a galaxy are not attached to each other like pieces of a solid wheel. Each one moves independently through the galaxy's gravitational field. What keeps them bound is the combined gravitational pull of all the mass inside their orbit. If the total mass is large enough, stars can move extremely quickly and still remain gravitationally trapped within the system. For a galaxy like UGC 12591, the enormous dark matter halo provides the deep gravitational well needed to sustain such high speeds. But even with this additional mass, there are still limits. If the disk of the galaxy rotates too rapidly, internal instabilities can begin to form. These instabilities do not usually cause stars to fly outward suddenly. Instead, they gradually reshape the structure of the galaxy. One common instability is the formation of a galactic bar. In many spiral galaxies, the central region develops an elongated bar of stars stretching across the inner disk. This bar can redistribute angular momentum throughout the galaxy. Gas and stars may move inward or outward as a result, slowly altering the structure of the disk over time. Bars are quite common, and they are not necessarily signs of failure. They are simply one way that galaxies adjust their internal balance. Another possible instability involves the thickening of the disk. In a stable spiral galaxy, stars tend to orbit within a relatively thin plane. But if the rotation becomes too extreme or if gravitational disturbances occur, stars can be scattered into slightly tilted orbits. Over billions of years, this can cause the disk to become thicker and less sharply defined. Computer simulations allow astronomers to explore these processes in detail. By modeling galaxies with different masses, rotation speeds, and dark matter distributions, scientists can observe how these systems evolve over time. These simulations suggest that spiral galaxies can remain stable across a wide range of rotation speeds, provided the gravitational mass of the halo is large enough and evenly distributed. UGC 12591 appears to sit very close to the upper end of that stable range. Its rotation speed is extraordinarily high, but the galaxy still maintains a smooth disk and organized spiral structure. This suggests that its dark matter halo provides just the right gravitational support to keep everything in equilibrium. The idea of an upper limit also connects with how galaxies form in the first place. If a dark matter halo grows extremely massive, the galaxy inside it may begin to attract other galaxies through gravitational interactions. Over time, mergers become more likely. These mergers tend to disrupt spiral disks and transform galaxies into elliptical systems. Because of this, most of the largest galaxies in the universe are not spirals at all. UGC 12591 may represent a rare case where the halo became extremely massive while the galaxy avoided major mergers for long enough to preserve its disk. Its environment may have been unusually quiet, allowing it to grow steadily without catastrophic collisions. The result is a galaxy that approaches the theoretical boundary of spiral galaxy rotation without crossing into instability. There is something quietly elegant about this balance. The stars of UGC 12591 move with incredible speed, yet they do so in harmony with the galaxy's gravitational structure. Each orbit contributes to a larger pattern that has persisted for billions of years. The galaxy does not feel chaotic or violent. Instead, it behaves like a vast cosmic machine whose parts move in precise synchronization. When astronomers measure these motions today, they are observing the outcome of a long history of cosmic evolution. The galaxy's extraordinary speed is not a temporary burst of activity. It is the result of countless subtle processes: gravity shaping dark matter halos, gas flowing along the cosmic web, angular momentum guiding the formation of disks, and time allowing the system to settle into equilibrium. In this sense, UGC 12591 does not truly defy gravity. Rather, it reveals just how powerful gravity can be when enormous amounts of invisible mass are involved. The galaxy reminds us that much of the universe operates beyond what our eyes can see. and that realization gently leads us toward the final part of the story. If dark matter halos can grow this massive and support such extreme rotation, what does that tell us about the invisible structure of the universe itself? By the time we arrive at the present moment in the story of the UGC 12591 galaxy, the pieces begin to settle into a larger and quieter picture. A massive spiral galaxy rotating at extraordinary speed is not simply an oddity in the cosmic catalog. It is a window into the invisible forces that have been shaping the universe for billions of years. The galaxy's rapid motion, its stability, and its immense mass all point toward the same conclusion. Much of the universe's structure is guided by something we cannot see directly. The dark matter halo surrounding UGC 12591 is not just an accessory to the galaxy. It is the foundation upon which the entire system rests. The luminous stars and glowing gas clouds that create the spiral arms occupy only the inner region of a much larger gravitational structure. Far beyond the visible edge of the galaxy, dark matter continues to extend outward, forming an invisible sphere that dominates the galaxy's mass. Inside this halo, the stars of the galaxy follow their long circular paths. Each star feels the combined gravitational pull of everything inside its orbit, including the vast unseen mass of the halo itself. Because that halo is so large and massive, the gravitational field remains strong even at great distances from the galactic center. This is why the outer regions of UGC 12591 can rotate so quickly without breaking apart. When astronomers compare this galaxy with more familiar systems like the Milky Way, the contrast becomes striking. Our own galaxy rotates at about 220 kilometers per second in the region where the Sun orbits the center. That speed already represents an enormous gravitational balance maintained over hundreds of thousands of light years. Yet the UGC 12591 galaxy pushes this balance even further, sustaining speeds more than twice as large across its outer disk. The existence of such a system suggests that dark matter halos can grow to truly enormous sizes while still allowing spiral galaxies to survive within them. This insight has important implications for how scientists understand galaxy formation across the universe. For many years, astronomers suspected that spiral galaxies might have an upper limit in mass and rotation speed before their structures became unstable or were destroyed by mergers. UGC 12591 demonstrates that this boundary may lie farther out than previously expected. At the same time, the galaxy reminds researchers that cosmic history is not uniform. Every galaxy carries the imprint of its own formation pathway. Some galaxies grow through dramatic collisions that reshape their structure again and again. Others evolve more quietly, slowly gathering mass over billions of years while maintaining their original form. UGC 12591 appears to belong to this second category, a system that matured gradually within an exceptionally powerful dark matter halo. There is also a deeper perspective hidden within this realization. When we look at a spiral galaxy through a telescope, we naturally focus on the bright stars tracing the graceful curves of its arms. Those stars feel tangible and familiar. They are made of the same kinds of atoms that form our own sunday. Yet in galaxies like UGC 12591, the visible stars represent only a small fraction of the total mass involved. Most of the gravitational influence that holds the galaxy together comes from something completely invisible. In a sense, the luminous galaxy we see is only the illuminated core of a much larger structure. The true shape of the galaxy is defined not by light, but by gravity. The stars reveal where matter shines, but the dark matter halo reveals where mass truly resides. This realization has reshaped astronomy over the past several decades. The universe that scientists once imagined as mostly composed of visible stars and gas now appears very different. Ordinary matter, the kind that produces light and forms planets, accounts for only a small portion of the cosmic inventory. The majority of matter exists in a dark form that interacts primarily through gravity. UGC 12591 stands as a particularly striking example of this hidden universe. Its extraordinary rotation speeds highlight the power of dark matter halos to shape the behavior of galaxies on enormous scales. Without such a halo, the galaxy's stars would not remain bound within their elegant spiral structure. And yet the galaxy itself seems completely unaware of the mystery surrounding it. It continues rotating steadily, its stars tracing silent paths through space that take hundreds of millions of years to complete a single orbit. Long before astronomers measured its motion, the galaxy was already spinning in this way, guided by the invisible mass surrounding it. In this quiet sense, the UGC 12591 galaxy offers a reminder about how much of the universe unfolds beyond our immediate perception. The light reaching Earth today began its journey hundreds of millions of years ago. During that entire time, the galaxy has continued its calm rotation within the deep gravitational well of its halo. And as we prepare to move into the final part of this journey, one final question begins to emerge gently from the darkness. If galaxies like UGC 12591 reveal the presence of vast invisible structures, what does that tell us about the universe as a whole? The answer may reshape how we imagine the cosmos itself. As the story of the UGC 12591 galaxy slowly unfolds, it begins to feel less like a puzzle about a single distant object and more like a quiet reflection on how the universe itself is built. What first appeared as an unusual rotation speed gradually revealed something deeper. A galaxy spinning faster than expected is not simply a curiosity. It is evidence of an unseen structure shaping the cosmos on scales far beyond the reach of human intuition. The stars of UGC 12591 move along their vast circular paths, each one taking hundreds of millions of years to complete a single orbit around the galactic center. During that time, entire species can appear and disappear on distant planets. Continents shift, oceans rise and fall, and civilizations briefly flicker into existence. Yet for the galaxy, these spans of time pass almost unnoticed. Its motion continues steadily, guided by the invisible gravity of its immense halo. If you could somehow watch the galaxy from afar over millions of years, the movement would appear almost gentle. The spiral arms would slowly rotate like the hands of a cosmic clock. Individual stars would glide along their orbits, maintaining the delicate balance between motion and gravity. Nothing would look violent or unstable. The galaxy would simply continue its quiet turning within the darkness of intergalactic space. This calm appearance is one of the most fascinating aspects of galaxies. Despite containing trillions of stars and unimaginable amounts of energy, they often behave with remarkable stability. Gravity acts as the organizing force, guiding the motion of every star and gas cloud. Even in systems as extreme as UGC 12591, that balance can persist for billions of years. The discovery of dark matter halos has changed the way astronomers think about this stability. Instead of viewing galaxies as isolated islands of stars, scientists now understand them as luminous centers embedded within much larger invisible structures. These halos form the true gravitational backbone of galaxies. The visible spiral arms are only the brightest part of a far greater mass that extends outward into darkness. In many ways, this realization transforms how we picture the universe. When we look at the night sky, we see points of light scattered across the darkness. Those lights feel like the primary actors in the cosmic story. But galaxies like UGC 12591 remind us that the most important structures may be the ones we cannot see at all. The dark matter halo surrounding the galaxy contains most of its mass. Without that invisible framework, the stars would not remain bound in their elegant spiral pattern. The extraordinary rotation speed that first caught astronomers' attention would not be sustainable. Instead, the galaxy would slowly unravel over cosmic time. Yet with the halo in place, the system becomes stable. Gravity quietly counterbalances the rapid motion of stars across enormous distances. The galaxy becomes a self-contained world of motion and balance, continuing its rotation long after the light we see today has left its stars behind. There is something peaceful about imagining this distant system continuing its slow cosmic rhythm. While our own lives unfold on timescales measured in decades, galaxies move according to clocks measured in hundreds of millions of years. Their rotation is almost meditative in its steadiness. UGC 12591 has likely been spinning in this way for billions of years already. Long before our solar system formed, its stars were already tracing their wide circular paths. Long after our sun eventually fades, the galaxy may still continue its quiet motion through the darkness of space. For astronomers, observing such systems is like glimpsing the long-term behavior of the universe itself. Each galaxy becomes a laboratory where the laws of gravity and cosmic structure can be studied across vast spans of time. The faster the galaxy spins, the deeper the gravitational well that must support it. In that sense, the extraordinary speed of UGC 12591 is not merely a record-breaking statistic. It is a clue about the invisible architecture of the cosmos. As we move deeper into the final part of this journey, the focus begins to shift slightly. Instead of asking only how this galaxy behaves, we begin to consider what its existence reveals about the universe as a whole. If dark matter halos can grow so massive, if galaxies can spin so quickly and still remain stable, then the unseen structures of the universe must be even larger and more intricate than we once imagined. And somewhere within that vast cosmic web, the UGC 12591 galaxy continues its quiet rotation, a distant reminder that the deepest forces shaping the universe often operate far beyond the reach of our eyes. As we continue drifting through the quiet story of the UGC 12591 galaxy, it becomes easier to see that its remarkable speed is only part of a much larger cosmic picture. A galaxy rotating at more than 500 kilometers per second may sound dramatic when expressed in numbers, but when imagined across the immense scale of space and time, the motion feels surprisingly gentle. Each star moves steadily along its path, guided by gravity and surrounded by countless others doing exactly the same. The spiral disk of the galaxy stretches across hundreds of thousands of light-years. From one side of that disk to the other, light itself requires hundreds of thousands of years to travel. Within this enormous structure, trillions of stars glow quietly, each carrying its own small solar systems, planets, and perhaps even distant worlds we will never know. All of them share the same vast orbit around the galactic center, moving together through a gravitational landscape shaped largely by invisible mass. If we imagine standing somewhere within the outer regions of UGC 12591, the experience would feel unexpectedly calm. The stars around you would appear almost fixed against the dark sky, much as they do from Earth. Their motion is enormous when measured in kilometers per second, yet because everything moves together within the same rotating system, the movement becomes almost impossible to notice directly. This is one of the quiet illusions of cosmic motion. Speed in space does not always feel like speed. When every object in a region shares the same orbital motion, the relative positions change very slowly. Even a galaxy spinning at extraordinary velocity can appear peaceful from within. This calmness is part of what makes galaxies so mesmerizing to study. Beneath the apparent stillness lies a vast choreography of gravitational forces. Every star is influenced by the mass of the entire galaxy. The dark matter halo exerts its silent pull across enormous distances, shaping the paths of stars that will never come close to one another. Over immense spans of time, these orbits slowly trace patterns that maintain the galaxy's structure. Spiral arms emerge as density waves moving through the disk, gently gathering stars and gas into luminous curves. Gas clouds collapse and form new generations of stars, while older stars continue their quiet journeys around the center. In UGC 12591, this cosmic dance has been unfolding for billions of years. Long before our planet formed, its stars were already moving through their great circular paths. Long after the present moment has passed into deep history, those same stars will continue their motion, guided by the gravity of a halo we cannot see. The idea that most of the galaxy's mass is invisible can feel surprising at first. Yet in many ways it reveals a deeper truth about the universe. Light allows us to see the bright surfaces of cosmic structures, but gravity reveals their true shape. The stars we observe trace the luminous outlines of galaxies, while dark matter defines the larger gravitational framework in which those galaxies exist. In this sense, galaxies like UGC 12591 are only partially visible. What we observe through telescopes is the glowing inner portion of a much larger system. The true boundaries of the galaxy extend far beyond the spiral arms, reaching into regions where no stars shine and where only gravity betrays the presence of matter. Astronomers often describe dark matter halos as invisible cocoons surrounding galaxies. Within these cocoons, galaxies form, evolve, and rotate. The halo of UGC 12591 may extend several times farther than the bright disk itself, quietly shaping the motion of stars across the entire system. Understanding this hidden structure has become one of the central challenges of modern astrophysics. Scientists have built powerful instruments to detect the subtle gravitational effects of dark matter. They map the rotation curves of galaxies, measure the bending of light from distant objects, and simulate cosmic evolution on enormous computers. Each of these efforts helps reveal a little more about the invisible framework supporting the universe. Yet even with all of these tools, much remains unknown. Dark matter continues to hide its true nature. It influences the motion of galaxies, but its particles have never been directly observed. Experiments deep underground search for rare interactions with ordinary matter. Telescopes scan the sky for clues hidden in cosmic radiation. Slowly, piece by piece, researchers hope to uncover what this mysterious substance really is. For now, galaxies like UGC 12591 serve as powerful reminders that the universe is shaped by forces we cannot see. Its extraordinary rotation speed becomes a kind of signature left behind by dark matter, revealing the presence of a massive halo surrounding the galaxy. And while scientists continue investigating these mysteries, the galaxy itself remains unchanged by our curiosity. It continues its calm rotation through space, stars circling their center in silence, gravity maintaining the balance between motion and structure. As the night deepens and our journey through this distant system continues, we begin to sense a broader perspective emerging. The story of UGC 12591 is not only about one galaxy spinning quickly. It is about how the unseen parts of the universe quietly guide the motion of everything we can observe. And somewhere in the immense darkness between galaxies, the invisible threads of the cosmic web continue stretching across space, linking countless galaxies together in a structure far larger than any single system alone. As the quiet rotation of the UGC 12591 galaxy continues across the darkness of space, it invites a different kind of reflection. At first, the galaxy seems like a dramatic exception, a cosmic object spinning faster than almost any other spiral galaxy known. But the longer we observe it, the more it begins to feel like a gentle reminder of how the universe truly works. Motion and gravity are always in conversation with one another, shaping structures that persist across timescales far beyond human experience. Every star inside UGC 12591 follows its own orbit, yet none of those stars moves alone. Each one is part of a vast gravitational community. The pull from nearby stars, distant gas clouds, and the enormous dark matter halo all combine to guide its path. Even though the galaxy spans hundreds of thousands of light-years, its components remain connected through this invisible network of gravity. In this way, the galaxy behaves almost like a living system, not alive in the biological sense, of course, but alive in the sense of constant motion and delicate balance. Stars are born within clouds of gas drifting through the spiral arms. Older stars travel slowly through the disk, carrying the chemical history of previous generations. Supernova explosions enrich the surrounding gas with heavier elements, preparing the material for new stars yet to form. All of this unfolds within the gravitational embrace of the halo surrounding the galaxy. The dark matter particles themselves remain invisible and silent, yet their collective mass shapes the entire environment in which the visible galaxy exists. Without them, the delicate structure we observe would not survive for long. This idea can feel almost poetic when imagined on the scale of the universe. The visible parts of galaxies glow brightly, catching our attention and filling astronomical images with color and structure. Yet the greater portion of the mass lies hidden, forming a framework that quietly holds everything together. It is a little like watching waves on the surface of an ocean. The waves are what we see, moving across the water and reflecting the sunlight. But the deeper currents beneath the surface are what truly guide the motion of the sea. In galaxies like UGC 12591, the spiral arms are the visible waves, while the dark matter halo represents the deeper current shaping the entire system. As astronomers continue studying galaxies across the universe, this hidden framework appears again and again. Spiral galaxies rotate in ways that suggest massive halos extending far beyond their visible disks. Clusters of galaxies remain bound together by gravitational forces stronger than visible matter alone can provide. Even the large-scale arrangement of galaxies across the universe seems to follow patterns shaped by dark matter. The UGC 12591 galaxy therefore becomes more than a single example of extreme rotation. It becomes a particularly clear illustration of how this invisible structure influences cosmic motion. The galaxy spins quickly not because it defies gravity, but because gravity itself is stronger than we might expect when the full mass of the halo is considered. Seen from this perspective, the galaxy's remarkable speed becomes almost peaceful. The stars are not racing toward destruction. They are simply following the paths allowed by the immense gravitational environment surrounding them. Their motion is the natural outcome of billions of years of cosmic evolution. If we could observe the galaxy over truly immense spans of time, its rotation would appear slow and steady, almost like the turning of a great wheel in the darkness of space. The spiral arms would drift gradually around the center. Stars would migrate slowly across the disk. The entire system would maintain its graceful structure while continuing its quiet motion. Meanwhile, the universe itself continues expanding. Galaxies drift farther apart across the vast cosmic web. New stars form while older ones fade. Dark matter halos grow, merge, and reshape the gravitational landscape across billions of light years. Within this immense unfolding story, UGC 12591 remains only one galaxy among countless others. Yet its extraordinary rotation offers a valuable clue about the invisible forces guiding the cosmos. It reminds us that much of the universe's structure is shaped by matter that cannot be seen, but whose gravitational presence can be measured through the motion of stars. And so, as our journey through this distant galaxy continues, the question that began this story slowly transforms. Instead of asking how a galaxy can spin so quickly, we begin asking something even more profound. What does it mean that most of the universe is built upon structures we cannot see at all? The answer to that question may take many years of exploration to fully understand. But galaxies like UGC 12591 quietly point us in the right direction, revealing the hidden architecture that supports the cosmic stage upon which everything else unfolds. As our quiet journey through the UGC 12591 galaxy begins to slow, it becomes easier to appreciate just how unusual our everyday sense of time really is. Human life unfolds quickly. Years pass, generations change, and even the longest human stories rarely stretch beyond a few centuries. But galaxies move according to a very different rhythm. Their clocks measure time in hundreds of millions of years, sometimes billions, and within that immense span their motion becomes calm and almost timeless. In the outer regions of UGC 12591, a single star may take several hundred million years to complete one orbit around the galactic center. That means the star may have circled the galaxy only a few dozen times since the universe itself was young. Each of those orbits traces a graceful path through the galaxy's dark matter halo, guided by gravity that has remained steady across unimaginable stretches of time. While that star continues its long journey, countless other processes unfold within the galaxy. Clouds of gas slowly collapse, forming new stars that begin shining for the first time. Older stars exhaust their nuclear fuel and quietly fade into compact remnants. Occasionally, a massive star reaches the end of its life in a supernova explosion, briefly outshining entire regions of the galaxy before its light fades again into darkness. Yet even these dramatic events are small pieces of a much larger cosmic story. The galaxy itself remains stable, its spiral structure persists, and its stars continue their silent rotation within the gravitational embrace of the halo. The immense dark matter structure surrounding the galaxy acts like a deep foundation beneath a city, holding everything together while the details above slowly change. From this perspective, the extraordinary rotation speed that first drew attention to UGC 12591 becomes less startling. The galaxy is not rushing or racing. It is simply existing within a gravitational environment that allows such motion to remain stable. The deep halo of dark matter provides the strength needed to keep trillions of stars bound together as they move through space. And somewhere far beyond the outer edge of the visible disk, that halo continues extending into the darkness. The stars fade away as distance increases, but the gravitational influence remains. Invisible particles continue orbiting through the halo, shaping the paths of the luminous galaxy at its center. Across the wider universe, countless other galaxies exist within similar halos. Some are smaller and slower, while others may approach the scale of UGC 12591. Each one occupies its own place within the vast cosmic web, connected by filaments of dark matter stretching across millions of light years. If we could step back far enough to see the entire universe at once, the pattern might resemble an immense network of glowing islands linked by invisible threads. Galaxies cluster along those threads, gathering where gravity has drawn matter together for billions of years. Between them lie enormous regions of darkness where very few galaxies exist at all. Within that grand structure, the UGC 12591 galaxy is only one point of light among many. Yet its remarkable rotation offers an important clue about the hidden framework supporting everything we see. By measuring how fast its stars move, astronomers have learned that gravity extends far beyond the boundaries of visible matter. This insight continues guiding modern astronomy. Telescopes scan the sky, searching for subtle distortions in light that reveal dark matter's presence. Computer simulations recreate the growth of galaxies across cosmic time, tracing how halos merge and expand. Particle experiments deep underground attempt to detect the fundamental building blocks of dark matter itself. Each of these efforts is part of a larger attempt to understand the unseen structure of the universe. And galaxies like UGC 12591 serve as quiet reminders that even the brightest objects we observe may be only small pieces of much larger invisible systems. As the story gently approaches its end, it becomes possible to imagine the galaxy continuing its rotation long after our brief moment of observation has passed. The stars will keep circling their center. The halo will continue holding them together. The cosmic web will remain stretching across the universe, guiding the formation of future galaxies yet to appear. And somewhere in that immense quiet darkness, the UGC 12591 galaxy will keep turning, its trillions of stars moving in harmony with gravity, revealing through their motion the hidden architecture of the cosmos. And so, as our quiet journey through the UGC 12591 galaxy reaches its final moments, the immense scale of the universe begins to settle gently into perspective. What first appeared to be a strange mystery, a galaxy spinning faster than expected, has gradually unfolded into something deeper and calmer. The motion of those distant stars is not chaos, and it is not defiance of gravity. It is simply the result of a vast gravitational structure surrounding the galaxy, most of which remains invisible to us. The trillions of stars within UGC 12591 continue their slow rotation around the galactic center. Each star moves through space at remarkable speed, yet the galaxy itself feels peaceful and balanced. The invisible dark matter halo surrounding it provides the gravitational strength needed to maintain that balance, holding the entire system together like a quiet foundation beneath a luminous city of stars. Far beyond the glowing spiral arms, the halo continues extending into darkness. There, the light of stars fades, but gravity remains. The unseen particles of dark matter move silently through space, shaping the motion of the galaxy without ever revealing themselves directly to our eyes. This invisible structure is not unique to UGC 12591. Across the universe, galaxies large and small exist within similar halos. Each galaxy becomes a kind of illuminated center within a much larger cloud of unseen mass. The stars we observe are only the visible portion of systems whose true boundaries extend far into the dark. Seen from this wider perspective, the universe begins to look different from the picture we might first imagine. Instead of a cosmos made mostly of shining stars, we find a universe shaped largely by invisible matter. The glowing galaxies are like lanterns suspended within a much greater web of gravity. That cosmic web stretches across unimaginable distances, linking galaxies together through filaments of dark matter. Along these filaments, matter slowly flows over billions of years, feeding the growth of galaxies like UGC 12591. At the intersections of the web, massive halos form, becoming the cradles in which galaxies are born and evolve. Within this vast network, the UGC 12591 galaxy continues its quiet rotation, one luminous island among countless others. Its extraordinary speed does not disturb the cosmic order. Instead, it simply reflects the depth of the gravitational well surrounding it. For astronomers, discoveries like this offer a glimpse into the hidden architecture of the universe. By studying how galaxies move, scientists can measure the unseen mass shaping their motion. The stars become tracers of gravity, revealing structures that would otherwise remain invisible. Yet even as these discoveries deepen our understanding, the universe continues holding many of its secrets. The true nature of dark matter remains unknown. We know it must exist because of the way galaxies behave, but its particles have never been directly detected. Somewhere within the darkness of space, the answer to that mystery continues waiting. Still, the motion of galaxies like UGC 12591 reminds us that the universe does not require our understanding in order to exist. Long before astronomers measured its rotation, the galaxy was already spinning quietly through space. Long after our observations fade into history, its stars will continue their journeys around the center. In that sense, galaxies offer a kind of cosmic patience. They move slowly, persistently, guided by forces that unfold across billions of years. Their motion is not hurried, and it is not chaotic. It is steady, graceful, and balanced. As you imagine the UGC 12591 galaxy now, far away in the darkness of space, you might picture its vast spiral disk turning almost imperceptibly against the black background of the universe. The stars continue their endless orbits. The halo holds them gently in place, and gravity maintains the quiet rhythm of the galaxy's motion. And somewhere among those trillions of stars, perhaps around one of them, distant worlds circle their suns, unaware of the immense gravitational structure surrounding their galaxy. Meanwhile, here on Earth, the light from UGC 12591 continues traveling across 400 million light-years of space, finally reaching our telescopes tonight. That faint light carries with it the story of a galaxy spinning steadily through the darkness, revealing through its motion the hidden forces shaping the cosmos. And as the universe continues expanding, the UGC 12591 galaxy will keep turning in silence, its stars moving in harmony with gravity, quietly reminding us that even in a universe filled with motion, there can still be a kind of peaceful balance.